me know. It should mention it to you. And I don't know if you all can see it, but in class here, we can actually see there's a little red dot going to the cloud that's increasing or decreasing in size. So please let me know because that has happened in the past where I've forgotten to start recording. All right. Just go through some tips before we go hot and heavy in the circuit analysis. And so hopefully this is a review for you all. But this is something even my fifth grader now, I actually recommend he does a lot of the things that we do in circuit analysis. And so I'll actually talk about some of the things over the summer because he had to multiply and divide numbers. And so he even talked about using factors of 10 to make it easier. But one of the best things you can do is check your units. If your units are what they expect, if you're looking for a current and you end up with a volt for your amps, you probably made a mistake, right? And usually it's not too much effort to add that additional feature into your work. So putting volts and amps and watts or whatever, and then understanding if I'm dividing a volt by a current, I get an ohm. So kind of knowing what that process is, it actually will really, really help you. If you want to go all the way to base units, that's actually where you can cross things out. The problem, though, is that actually requires you to have a deeper level of knowledge of the different units. So like a volt is not an SI unit, so you don't necessarily know what the corresponding unit would be so that when you can cancel things out. But we'll give you a little bit of that here. And again, you can always go back to it. One really good thing, there's a program called MathCAD, and MathCAD does built-in unit conversions. It takes a lot of effort to set it up, so I don't know how much it is worthwhile. But if you really wanted to do like perfect unit checking, you can always use applications like MathCAD. MATLAB, I don't believe, has that capability in there, but I know MathCAD does. So you want to always try to go back to your base units if you can. In electrical engineering, our base units are volts, amps, ohms, and watts, right, are generally our base units. And then sometimes, depending on what type of analysis you do, you might end up with farad or henries, right? Because those aren't exactly impedances, right? You got to do some conversion there. And then you may start to get into maybe more advanced analysis where you start looking at frequency, where you actually start including the J omega terms, right? When you look at complex terms. So it just depends on what level of analysis you're doing. The base unit we can always go, everybody understands, is time, right? Seconds. So if you use seconds, that's a pretty baseline one that works really well. And then the prefixes for orders of magnitude, right? We're hopefully pretty familiar with that. But the reason why we do that, and again, this is something I taught my son over the summer, which is if you're trying to take 10 kVA and multiply that by 1K, it's maybe not obvious that you're going to end up with a mega in there. But if you take it to the actual multiplication, so K or kilo is the prefix that corresponds to 1 times 10 to the 3. And if I go 10 times 10 to the 3 instead of 10K, and 1 times 10 to the 3 instead of 1K, then I can, because everything is multiplying, I can just move things around and I can put the two 10 to the thirds together. And when you are multiplying exponents, you just add the exponents together. So what you end up with is 10 times 10 to the 6 or 10 MVA. All right. Same thing for dividing. If you wanted to divide 10K by 1K, you'd have 10 to the 3 divided by 10 to the 3. So how does that work out for us? How can we figure out how to do that? Well, if multiplication is adding, division is subtracting. Or you can also bring that up into the numerator, so it's not a division. And 10 to the third in the denominator is just 10 to the minus 3. So when these get put under, one exponent, that's just 10 to the 0. What's 10 to the 0 equal to? Just 1, right? So really quick and easy way when you're dealing with bigger numbers or even smaller numbers, you can check your work and say, am I getting things correctly? again, it might be something old hat to you, but doing it this summer, I was like, wow, that's really cool, because divide by 10, multiply by 10, they start to do that in fifth grade. And we do it in engineering, but we don't even think of it because we just use mega and kilo and all that stuff. So sometimes we forget that we can just do the basic multiplication and division that we have there. So here are some base units. These are actual, if you go to not SI, but if you go to the very base, what we'll see is we have meter, kilogram, second, and amps. Also, you can do Kelvin for temperature, mole, which is a chemical number, and candela. Anybody know what a candela is? When you think of candela, what word is buried in candela?
Light intensity.
What's that?
Light intensity.
Yeah, a candle, right, puts out a certain amount of light. So a candela is a measurement of light intensity. And normally it's done in foot candles is the typical one that you would see. But yeah, that's a measurement of light intensity. So if you're designing, like many years ago, most of you all probably didn't realize it, but when they built the Home Depot and the Walmart in Bangor, those parking lots are built with pretty specific lighting. Car dealerships, I've never done a car dealership, but car dealerships even more. Why is it? Why is car dealership? Why is lighting so important?
The cars have to look good on the lot at
When you
night.
see the cars at night, what does that mean to see the cars at night?
Someone drives by at night, when you see a car, they like go and make it in.
That's it. But what's really important about seeing cars at night? It's the color, right? So if you were to go to parking lots not that long ago, they had a really bright white light. Whereas if you go to some of the less important places, it was kind of a orangey yellow light. And the reason why they go with a bright white light is because it actually helps you so that you can see what's called the color rendering index. You can actually see what the color looks like relative to even in the broad daylight. And so we live in Maine. It gets dark at 4 o'clock in the winter. You're doing car shopping at night. It's the same thing. Home Depot and Walmart now do that, but for different reasons, right? You're not buying products outside. Why would you think color is so important at the Home Depot and Walmarts of the world?
Red vacation.
Yeah. What if some bad guys are trying to, steal a bunch of stuff? Hey, this person's taking off in a red, whatever, and they're wearing a blue shirt. So by having that ability to do color rendering, it makes it much more effective for them for doing that. The other thing that's really important, and this is one of those things that people don't understand, if you're at night and you're walking to an area and you want to go shopping, if it's dimly lit, it just gives you the feeling of it's not as well maintained, it's not as safe, right? And again, it's hard to say if you're in Bangor, Maine, because it's particularly safe, but maybe go to the southern part of the state. Maybe there are towns that aren't as safe, that if they're not well lit, you might think twice about going to those stores. But going to a Walmart or a Home Depot, it's so well lit, you drive in and you feel instantly safe. You don't have the same level of concerns that you would otherwise. And so there's a lot of design effort in actually laying out the lighting at those facilities. And the other big thing too is a lot of cities have ordinances that you can't exceed 1 foot candle at the property lines. And the reason being is because if I have a house and I'm right next to a Walmart, I don't want it to be, almost like daylight because at nighttime, because it's such bright lights. And so you have to do a lot of stuff in the permitting process to make sure that that works. But there actually are there's a lot of engineering in the light fixtures themselves in terms of how they aim and throw light. So it's really, if you want to get more into it, I used to do a lot of that. I don't do that much anymore. Actually, I don't do it at all anymore. But there are people that they do it. And architects in particular, they really can throw lights in different ways and they can really change the perspective of things. So our energy is going to be a joule. And then our rate of doing work or rate of energy consumption is a watt or a joule per second, right? Going down to its base units. So charge, we always have charge and we conserve it. So we don't destroy an electron or a proton. We just kind of conserve it and we just move it from one point to the other. That's what electrical circuits are about, is moving energy via electrons and forcing them to go in a specific spot. So when we measure charge, we use a coulomb, right? And the unit for that is a coulomb or C, but we typically represent that in equations as either uppercase or lowercase q. Either one I've seen, it depends on your physics book. Most of the ones I've seen tend to use a lowercase q. But yeah, you get the idea. What is the level of charge for an electron? 1.602 times 10 to the negative 19. Okay. So that's the smallest amount of charge you can have. You can't break anything smaller than an electron. And in most circuits, the actual flow of charge is based on where do the electrons go. There are other devices that it's different. Anybody want to guess as to what those are? You've just taken a class with John Allen that he would be able to tell you. Semiconductor theory, the concept of holes, right? So you can get hole flow or electron flow. And so when you create a hole, you're basically meaning that there's an electron that is gone from there. And so then you hopefully will have an electron that fills that. So there's hole flow or electron flow. We're not going to get too much in electronics in this class, so we'll really just focus on the flow of electrons. And everybody understands that current flow is in the opposite direction of electrons. That's our conventional current flow. But in fact, all our current flows in the opposite direction. It flows in the direction of electrons. So even though we say positive current flows out of a power supply, in fact, the current actually flows with the electrons, so it goes out of the negative. So if you were actually to monitor the electrons, right, that's where the current, that's where the energy is flowing, it actually flows out of the negative terminal, not the positive terminal. It has to return to the positive terminal. So it goes out the negative and returns to the positive. And so depending on where you took circuit analysis, there's conventional current flow, which is positive and positive current, or electron flow, which is positive, is out of the negative terminal. So not a big deal, but just in case you're really trying to understand a little bit more depth. So current is rate of charge flow, how much charge is moving over time. So an amp is not an amp. It's really a coulombs per second or a coulomb per second. How many coulombs per second that you have flowing typically through a wire. And what we'll learn as you get more and more into circuit analysis and looking at magnetic circuits is we almost always assume that current will flow through a conductor, right? And the reason being is because the insulation level of just the air itself, right? If you just look at air, the insulation level of air is really quite high. So it's not typical that electrons will flow through the air. They do a little bit, right? You can see static electricity as an example. If you walk by a substation, sometimes you can hear some crackling. If you take a capacitor and you just leave it on your desk, it'll discharge a little bit. Sometimes that's internally, but you can get electrons that flow through the air, but very, very limited. So almost all of them will be captured in a conductor. Our conductors are almost always circular in shape. Anybody know why? They don't have to be.
Outer shell.
That's the skin effect, and so that's part of the reason. Yeah. Anybody else want to guess? Electricity is not like sharp edges. If you've ever walked into a substation, you don't see square things having or having current or voltage anywhere near them, because it'll start to bleed electrons through the air. It'll go around, and then you'll actually get corrosion. Essentially, will delete the material. So almost all current carrying devices either are circular or will have round edges. Even insulators, they tend to be round edges because you're trying to reduce the corona effect. Yes, sir.
These bus bars, are they usually around?
Excellent question. So for those of you in TV land can't hear, the question is bus bar. What is a bus bar? What is a bus? Well, it's a common connection typically. We often refer to them as a node, right? But a bus is usually where you can either take off or go into a common bus. And so it's electrically considered a node. And when you build either a switchgear or a substation, you have inside of the structure, you'll have a bus. In a utility structure, it'll be aluminum. And it's usually like a 4-inch circular pipe with an open center for the skin effect. Inside of a switchgear, they'll usually use like a rectangular, sometimes a solid piece, sometimes they'll actually use sheets of copper typically. Anybody know why they use aluminum outside and copper inside? Corrosion, yeah, that's all it is. Like you can leave aluminum outdoors, and as long as you're not next to the salt water too much, corrosion is almost minimal for aluminum. Where copper, it's corrosion proof, but you do get that patina, and you do get some effects that it's not as effective. But the bus bars inside those switchgear tend to be more rectangular, but even then, their shapes around. And the biggest reason, a substation is big, right? It has lots of room. Where a switchgear is going to go inside of a building typically, not always, but usually inside of a building. And so space is at a premium. So inside of a switchgear, you'll actually try to limit the amount of space that you have until you go into much smaller ones. And so copper bus bars usually tend to be rectangular for space savings. Also switchgear, most of the time you're talking medium voltage, 15 kV or less, and you're not talking 345 kV. You can if it's GIS. But for the most part, you're talking medium voltage stuff if it's solid dielectrically insulated. And so you don't need to have, you don't need to worry too much about the corona effect because the voltages tend to be so much smaller. So that's the biggest reason why bus bars are usually outdoors, will be rectangular, and inside of a switchgear, it's for space and you don't have corona as much. Those are the two big reasons. Good question. So yeah, we're just monitoring individual charges going through a specific area. And it's a specific cross-sectional area. Voltage, what's the definition of a voltage? Well, the voltage, so this is the definition, it's key to understand. So 1 joule of work required to move 1 coulomb of charge from point A to point B is the equivalent of 1 volt. So if you think the understanding right, it's 1 joule of work required to move 1 coulomb. So what would the units be for voltage? It is 1 joule of work for 1 coulomb, right? So the units would be joules per coulomb. That's how many joules per coulomb that you need would be the units for voltages. And what's interesting is that the voltage can be positive or negative because the voltage is always a potential difference, right? You're looking at 2 points. So when we measure voltage, sometimes you've heard the word potential. You've got to measure across 2 points. So you can see that if I've got a plus, let's do the first one, A. I have a minus 5 volts. That means my current would be going in the opposite direction for our conventional current flow. We can swap the polarity around. We can make it minus to plus, right? And then have a positive 5 volts, just as a reference perspective. Or if we have a voltage that is as shown below, we can have plus to minus with a positive 5 or minus to plus with a minus 5. It doesn't matter. You can swap the two around. Power is the work required to push a current, an amp, 1 amp of current, which has the units of coulombs per second, into a voltage, which has the units of joules per coulomb, and its units are in watts. So let's check that out. So my power equation is V times I, which is a joule per coulomb, times a coulombs per second. Let's check our units. We know that work is the number of joules per second. Our coulombs will cancel out. And we are left with joules per second. Okay? So that is the amount of current. The amount of the current times the voltage. So that's the amount of work that is being done. Now, if I look at this blob, can I tell if this blob is a power source or a power load? Or can you not tell? Is the blob a source or a load? What is it? The blob is a load? How can you tell? Current's going in? Everybody agree with that? Anybody disagree? Not sure if you want to disagree? I will disagree. Because knowing the current direction is not enough. You need two pieces of information. If it's a source, what does that tell you? You're putting energy into the system, right? You're increasing the energy. So if I increase the energy in the system, don't I need to increase the voltage in the direction of the current flow? So if the voltage increases in the direction of the current flow, the only way that can happen is I'm putting energy into the system. If the voltage decreases in the direction of current flow, the only way that happens is I'm pulling energy out, right? That whole concept of doing a 1 joule of work per coulomb. So I need two bits, two pieces. I need to know the direction of the current, and I also need to know the potential, the positive to negative which voltage. So in this case, the blob is in fact a load, but I need to know that it's a load because the current is going in the direction of a voltage drop, not a voltage rise. Okay. Can sources and load, can you have a device that's a load or a source? Not at the same time, but can you make a device that does that?
Yes,
Can a load be a source? Can a source be a load?
Like,
Capacitor, maybe, right? You can store electrons or you can discharge them.
a
We
recharge.
talked about this the other day. If you have big fancy stereos, sometimes you need the bass boost, so you use a capacitor.
motors and alternators.
Motors and alternators, say more. Not sure.
Well, you typically use certain types of motor paddle.
Yep. Anybody here have a hybrid vehicle? I have one. How do you have a hybrid vehicle? How does a hybrid vehicle work? Regenerative braking. So what does that mean? You put the brakes on and then it regenerates. What does it do?
Yeah.
What's that?
Yeah.
It can, but also when you apply the brakes, you can also slow it down too, right?
So pushing energy into the motor, to allow the motor to push energy back.
So at that point, it's not a motor, it's a generator, right? We change the title. But is it a different motor or is it the same? Is it the same piece of machine or is it different? Same machine. So you can actually have that machine, we'll call it a machine because it's a generic term. And that machine can either act as a load, like when you're accelerating and you're trying to get the car to go up to speed, or it can act as a generator and it can suck power and put it back into the battery. Any other one?
What
So
about,
some of you have hybrid vehicles. There's another one that you have.
Paul, what about the rechargeable battery?
Yeah. How about your car battery? You walk in, you start the car. That's a source of energy, isn't it? It turns the starter and it turns, hopefully starts your car and you can take off. But what about most of the other time? You have an alternator. I would have said you would have had there's a buck boost converter on my car. I don't even have an alternator in my car because it's all done through the regenerative battery system. But you actually would charge the battery when the alternator is running. Unless you really have got too much load, then you'll be charging your battery. So a battery, a rechargeable battery, is a perfect device that can act as a load or a source. And you can see it too. Like sometimes when you're driving your car and you put on a lot of loads and you can see the headlights dim, probably not so much anymore. But on older cars, I remember having an older Subaru that I left the lights on in the car and I had to get a jump start. And so I was letting it, because it was in the winter, so I was letting it run because it was running, and I would let it run with the lights on and the heat, the rear defroster going and the front defroster going. And then after I had done that for a few minutes, I'm like, okay, it's time to take off. Well, the car stalled immediately because it was too much load for the battery. So older cars, the alternators weren't big enough to be able to do that. Even today, you can go out and buy a Ford pickup or a Chevy pickup truck that has an alternator that's good for what, 110 amps, 140 amps. Some of the smaller cars, 40 amps. So you don't have that much load, you can get by with smaller. But alternators, usually the alternator is one direction only, but we call it a machine to make it generic. So that's the thing. To be able to tell if something is supplying or absorbing, you need to know both those parts. All right, so these are pretty quick and easy. We can see that the blob in A is going to consume 6 watts or supply 6 watts? Well, we know VI is 3 times 2, so it's 6. And it is absorbing power because in the direction of current, the voltage is decreasing. How about in B? In B, we have negative 3 amps going in the direction of negative 2 volts. So the way to tackle this problem is don't treat that as a negative 2. Treat it as a positive 2, which means I have to switch the plus and the minus. And I'm going to do the same thing for the 3 amps. It's a negative direction. So I'll change the arrow and then just make that a positive 3. So does that add more clarity if this is absorbing or supplying power? So if it does, which one is it? Is it absorbing or supplying power?
Absorb.
Yeah, it's dropping current in the direction. I mean, it's dropping voltage in the direction of current. So this is absorbing. How about the last one? Switch directions. Call it 5 amps. Absorbing or supplying? Supplying, because in the direction of the voltage drop, it has a positive current flow. So if you ever get confused, just swap the polarities. That's all you need to do. It makes it much, much easier. So because it's a calculus-based class, it's calculus, we got to use it. We got to get comfortable with it. How do we determine the work? So we can just integrate over time. So a 100 horsepower motor is designed to provide 100 horsepower for 40 years continuously. That doesn't mean it actually operates continuously. That just means it is providing, or it has the ability to provide that. So that is 100 horsepower, which we can convert to watts. How do you convert horsepower to watts? Multiply by 746 watts per horsepower, right? So you're almost at 75,000 watts, essentially. But the problem with that is that that's the rating. We actually want to know what the joules are, not the joules per second. So we have to take our power and then integrate that over our period of time. Okay. So to go from work, we have to integrate because the rate of power can be varying over time, right? It doesn't have to be a constant power. It can be varying. So that energy determines your electricity need or how long your battery will last. So when you buy a battery, you're buying a 12-volt battery, but it's also rated on amp hours, which is a more important value because that is essentially telling you, how much storage capacity can I have. Batteries also have something called cold cranking amps. That's not as useful. That just tells you like what the battery is able to deliver under sort of short circuit conditions, if you will. So if it's a cold battery, what's the resistance gets to be a lot higher in a battery. So how much current can it possibly provide, to be able to start up a fairly big load? But the most important thing is amp hours, right? If you're going to run, not necessarily so much for a car, but if anybody is here into boating, sometimes you shut your boat down, and you crank up music and you do whatever you want to do for hours on end. That battery, it's much more important because you're not connected. You can't get a jump start, right? So you got to have a lot more capacity in that. And so electric vehicles today, that's the biggest thing is their capacity. So amp hours is a much more useful one for that. So here's an energy example. So how many joules are in a watt hour? So it's 3,600. So for what you pay for in your utility bills, because you pay for kilowatt hours, every time you pay or use a kilowatt hour, you use 3.6 megajoules. Okay. So a kilowatt hour actually is quite a bit of energy. But our battery capacity, as we mentioned, is in amp hours. And so you just multiply the battery voltage by the capacity, and you can end up with a 2 amp hour capacity, which corresponds to 10.8 kilojoules. Okay. So you can technically supply the circuit for a 200 milliamp or 0.2 amp circuit for about 10 hours. Now, in reality, you're not going to be able to do that because the battery is going to drop so low that it's not going to be effective. but you're gonna have to come up with some typical values, and, we use that as, values there. All right, so voltage sources, easy peasy, right? We like voltage sources. And if it's a voltage source, the one thing that's unique about a voltage source is it dictates the polarity, okay? So when you have a voltage source, you have two things you have to provide. Number one is the magnitude of the voltage source. Is it 10? Is it 500? Whatever it is. And the other really important thing is the polarity, because the rest of the circuit does not determine the polarity. You, by plugging that in and connecting it a certain way, determine what the polarity. So you need to specify the plus and the minus. And for an ideal source means it'll do everything within its power, including burning itself up, to maintain whatever voltage you have. So if you have an ideal source and you put a dead short circuit across it, it'll, in an ideal world, it'll be able to maintain that voltage at whatever value it is. Now, that's not realistic, right? Because a dead short circuit has 0 ohms of resistance. So you can't get a voltage across it. But let's say it's 1 milliohm. The ideal voltage source will put out millions of amps if necessary to go ahead and maintain that voltage. That's why it's ideal. It only represents in paper. What we often do in the real world is we model, well, let me back up. Let's see if you know this. How do you model a system in the real world? There's no such thing as an ideal voltage source. So how would you model that? How would you model an ideal voltage? Anything in the real world to represent what is actually happening. You put the voltage source, that's ideal. And then normally you put a resistor across it, right? And as you increase the voltage, the current out, the voltage drops. So the more load you draw, the lower the voltage is on the terminals. And so what we do in many cases in circuit analysis is we're really good at Thevenin and Norton and doing all that stuff, or we will be at the end of the semester. But the idea is that we take a real world circuit and we model it with ideal components so that we can analyze them. So we can use ideal voltage sources as long as we put those resistors in there. And this happens all the time. If you go and look at the utility system, which, can do hundreds of thousands of amps, all these individual generators actually have, you can model them as an equivalent impedance with a voltage. So like campus, you can actually look at the Versant power system coming in, and there's a voltage and an impedance in series with that voltage. And that's actually how you can calculate different parameters on it. So the voltage determines the magnitude as well as the polarity. The current out of that is all dictated based on what the load looks like. Okay. And an ideal voltage source means it can supply an infinite amount of energy, but it also can absorb an infinite amount of energy. Remember, all a voltage source is trying to do is keep the voltage fixed. So if it has to crank out electrons or absorb electrons, it should be able to do both, right? So that's why we can flip-flop the direction of current, and the ideal voltage source should be able to handle that without any problems. A current source is similar, but slightly different. So a current source is having two parts you need to know. Part one is the magnitude of the current that comes out. And the second part is the direction. Okay. Is it up or down? Those are the only two things that you can dictate in a current source. Everything else is based on the load. So the voltage drop across the load can be plus to minus, that direction, or that direction. The current source doesn't care. It'll act as a source or a load. Doesn't matter. It's all based on maintaining the current. So here's why these are very important. Because if you go in with the fact that understanding a voltage source, its whole job in life is to maintain that polarity voltage. Or a current source, its whole job in life is to maintain that current magnitude and direction. Everything other than that allows you to use those as reference points. So when you're doing circuit analysis, those two things you always can go back to, and it makes your rest of your circuit analysis easier because I basically have references, if you will. I know this to be true. Then we get to those dependent sources, and boy, oh boy, dependent sources make things a lot more complicated because they are dependent upon something else that's in the circuit. And you can have dependent current sources or dependent voltage sources. Are there any devices that you all have studied to this point that you've had to study dependent sources pretty extensively? I know our EET students here should have. At SMCC, do they do electronics courses?
Yeah.
Was there a dependent source in your electronics course?
Not that-
Anybody? How about a dependent source in a BJT? Isn't the BJT equivalent circuit model including a dependent source? Y'all remember that? Why is that so important? Because remember, the current going from emitter to collector is based on the amount of current going from the base to the emitter, right? So if you measure that current, you can actually calculate reasonably accurately what that output is going to drive to. So it's a dependent source. You all remember that? Let's see. Let's see if I can bring it up. Let's see if I'm joshing you. And I just did this randomly, right? That's a pi equivalent, but you can see a dependent current source there, right? Want to look at another one? Let's just do images here and we can see a bunch of images. Right here, right? This is somebody's notes. Over here, they use a different representation. They use a circle with a K multiplier. Normally, you would use the diamond symbol to represent dependent sources. So if anybody not seen dependent sources, just needed to jar your memory. If you haven't, that's okay. We'll do the circuit analysis necessary, but you have to do dependent sources primarily for electronic devices. Got to do those a lot. All right. Find VL below. Pretty easy, right? So it's got a dependent source, and the dependent source is 5 times V2. The voltage V2 is the actual controlling variable for that dependent source. And so we got to look someplace into the circuit and find what V2 is, or have some way of finding what V2 is. And we happen to see that V2 is equal to 3 volts. So 5 times V2 is 15. And since VL is looking across a common node, we can see that VL is just 15, 3 times 5. It's the same thing as the dependent source. Easy one, so we won't spend too much time doing that. You don't have to copy these down. These are all in the notes. You're welcome to if you want, but these are all in the presentations that hopefully everybody has access to. Ohm's law. This is for linear applications, and this whole semester, and probably most of your college career, almost all your college career, is going to assume things are linear, because if they're nonlinear, it makes things way more complicated. So we'll assume that the resistance is a linear element, meaning it's going to, whatever voltage or current, whatever voltage drop you see, whatever current through there, that resistance value is fixed. So V equals IR is Ohm's law. We'll modify that, right, to V equals I times Z. Or we'll even do things in Laplace, where we'll include variables like S, the S operator. So unit of resistance is an ohm. Can you tell me what the base unit of a resistor is? V divided by I. What are the units, the base units for volts? Joules per Coulomb. What's the units of current? Coulombs per second. Fractions within fractions. All we need to do is invert and multiply. kind of an ugly one, right? So that's the unit of an ohm. You certainly are welcome to check the units there, but you can see that that gets to be, that's why I said sometimes it's usually easier to use volts, amps, and ohms to do your unit checking instead of going all the way down, because this one takes a little bit of effort to do that. So we can derive, and if we need to do this, let me know. I don't, hopefully don't need to, but V equals V times I, which can either be V squared over R or I squared times R. If you had to pick, which one is usually the most useful of those? V squared over R or I squared times R? Yeah, I squared R is by far the easiest one to use, because to calculate V squared over R, you need to know the voltage drop across the resistor. Okay. And in many cases, people forget that voltage needs to be that across that resistor. They assume like it's across a bunch of elements, and so they use V squared over R. But if I use I squared R, I know that I have to use the current that is in fact through that resistor. So it's almost always better to use I squared times R. One other thing about P, you notice it's lowercase or italicized, depending on your perspective. That's really important because that's called instantaneous power. At any instant in time, it's equal to V times I at those instances in time. So a better way to write this, but I don't because it would get really busy. You write it V of T times I of T. So as long as you have the right time for both the voltage and the current, you can find that value. Because we know in AC circuits, it doesn't work this way, right? It's a lot more complicated. So we have to make sure that we understand that those are instantaneous values. So power is, when we reference power, it can be positive or it can be negative. Like in the case of a source, right? If we want a 12-volt source and we say that that's a 5 kilowatt source, then 5 kilowatts going out of the power, going out of the load is, or the source is positive. But how can the power going into a resistor be positive as well when it's consuming power? Shouldn't they be the same? I have a box here. Is power positive or negative there? Positive. You sure? Yep. But what if this is a source? So in a box, right? So here's the hard sort of tricky thing about if power is positive. It usually is based on coming up with some assumed value. So if I have a source here, we assume that P is going out of the source, right? Then I and P will be going in the same direction. So those will be both positive, right? In the assumed direction, we pick out of us, we call this a source. So P is out and I is out. If it's a load, and now I'll just draw a box. In a load, we assume P is in and I is in, and those are both positive as well. So you can have negative power or you can have positive power. It just depends on what you're determining, if it's a source or a load. All right. So that adds a little bit of complexity, but we know that loads always consume power and sources always supply power. But if for some reason that assumed load is actually supplying power, then power is out, it's negative. Can you give me an example of a device that is, we normally treat it as a load, but actually can supply power? Somebody said it earlier in our example of a source. Capacitor, right? Oftentimes a capacitor, you're trying to charge up the capacitor, so you treat it as a load. It's absorbing power, storing energy. And then when we need that energy, the power goes in the opposite direction. We haven't now called it a source. It's still considered a load, but the power is in the negative direction. So when we start to look at charging and discharging of capacitors, you'll actually see the power will go negative. What can never go negative in a capacitor? Or even a source for that matter, but a source is a little harder to see. No. How about the work? Can you ever have negative joules in a capacitor? No, the energy has to come from somewhere. So when you're analyzing a circuit and saying, well, my capacitor has negative 12 joules of energy stored, you might be like, uh-oh, where did I get the joules from, right? That's not going to work so well. So you can get to zero, but you can't get negative. So here's a simple example. 560 ohm resistor is connected to a circuit. Once that 560 ohm resistor is connected, you get 42.4 milliamps to flow through it. We want to calculate the voltage across that resistor and then the power that that resistor dissipates, all right, or consumes, depending on your perspective. So Ohm's law tell us V equals I times R. We get just under 24 volts. And again, since we know the current, we'll just use the I squared R here. So I squared, 42.4 milli squared times 560 is just slightly over a watt. Another term, and as you get more advanced in your analysis, you will use the term conductance way more because we actually live in a parallel world. And what I mean by that is the outlet over there is connected in parallel with the outlet over here, et cetera, et cetera, et cetera. So most loads tend to be connected in parallel, so they'll have a constant voltage. So using conductance actually makes a lot of our calculations much, much easier. So conductance is the reciprocal of resistance. So 1 over R or 1 over an ohm has the units of a mho, right? The inverse of an ohm is a mho. That's only if it's purely real. Okay, actually not purely real, it can be imaginary. So it can have mho. If it has a complex term, we can also call it Siemens. So instead of having Henrys and all that stuff, we can also use the term Siemens. And conductance is how good of a conductor it is, right? So if you have a very high resistance, that means you have a very low conductance. If you have a very high conductance, that means it's a darn good conductor because the resistance is low. And anybody here work in the process industry ever? Process is like making paper or other types of products. All right. So you may have come across a device that's called a conductivity meter.
We had to install a couple at Saturday.
Oh, perfect. What does a conductivity meter do? What's its job?
We'll see how conductive whatever going through that pipe is, but
What would be going through the pipe?
it'd be, I think we put it on like sweet black liquor.
Black liquor,
Yeah,
maybe even sometimes water?
yeah.
Why would you care how good of a conductor water is? Water is a good conductor, relatively good conductor, right? Remember swimming in the pool when you were a kid and they had a thunder boom out there and everybody had to run out of the pool because you could die if a lightning bolt happens. So water is a good conductor, isn't it? Actually, it's a really bad conductor. Pure water is the worst. It is terrible. But water that we drink has lots of dissolved metals in it. So that's actually what makes it a really good conductor. If you're at a paper mill and you want to have a system that's not going to have a lot of corrosive stuff, right? Because a lot of metals and a lot of stuff in the water mean it can corrode pipes. You want to clean the water up. But if the water is too clean, it actually will strip the metals out of the pipe because water likes to, have metals dissolved in it. So if you were to just drink distilled water the rest of your life, your bones would break essentially or fall apart because it would strip all the calcium out of your bones. That's why you can't just drink distilled water. You've got to drink water and you have to add some mineral tablets in it. So conductivity measurement is a way of telling you how clean the water is. And you can't be too clean and you can't be too dirty. So you're trying to find a medium, and usually they have alarms. Hey, the water is at the right conductivity level, which just means how electrically conductive it is. So how do you detect conductivity? You run a current through it. And if the current has a certain value, its conductivity is really good. If it runs well, then its conductivity is really good, which means the water's dirty. If hardly any current flows through it, it might be too non-conductive, too clean of water, which can be bad as well. So you have to find that happy medium, and you do that all the time. So pulp and paper plants, steam turbine generators, wherever they use a lot of water, it's essential that you make sure that the water has the right level of cleanliness. And a conductivity meter is what they use. Been used for many, many years. Nodes, paths, loops, and branches. A node, by definition, is any two or more devices connecting to a common point. A common point means there's no potential difference between those points. So you can have 2 or you can have 2 million. It really just depends on what you have. So that is a node. A path is a way for current to flow through and from a node. So if you have a path, current can run through that path and go someplace else in your circuit. A loop means a closed loop. So all the current that starts at the beginning of your loop has to end up at that same spot. It is a closed loop, and all that current needs to flow through there. And then a branch and a path are almost the same, but usually a branch is just a break off from a node. So it's like a tree, right? If you just can imagine that you have a branch going someplace else on a tree, it's similar, except you have to close the loop so that you can have current flow. So you can see here, I have 1, 2, 3 nodes because I have 2 or more devices connected to a electrically common point. And then I can start to look at different branches, right? 1, 2, 3, 4 branches. For loops, I have almost an infinite number of loops. We go that way. And then the branches or the paths are pretty much the same, okay? So a loop is pretty much any way you want to denote that. So once we have the concept of nodes, paths, branches, and loops, we can start to use KCL. Now, this is where I need your help, because I used to love to say the sum of the currents in equal the sum of the currents out, but that's not what most of you have learned. How do you prefer to do it? I say this. That's how I do it. But I think what most people prefer, even though it's the same approach, I forgot the I, or some of the outs and minus the sum of the ends. Do you have a preference of how you like to do that? I think. So item number 1 here. Yeah. Anybody do item 2? I think most of the way that John and Jude teach is they do item number 2.
Yeah, we learned it that way, but I think I know about that.
Yeah, to me, I like to say, because the gazintas is equal to gazatas, it's a silly way to do it, but it's the same approach, right? It's just algebra to go sum of the ins minus the sum of the outs equals 0. It's saying sum in equals sum out is the same thing. So we'll try to stick with 1. If it causes us any heartburn, we'll go ahead and we'll modify it, okay? But in this problem here at the bottom, we see that that is the sum of the current in minus the sum of the current out equals 0. So current in is all based on direction. So IA plus IB minus IC minus ID is going to equal 0. And we know that Kirchhoff's current law is true because it's conservation of matter. What is conservation of matter? Do you remember that? All matter has to be accounted for, right? So if I'm stuffing electrons into this node, and they're not allowed to be stored there. All those electrons have a mass associated with it, right? It's a small mass, but it's a mass nonetheless. And so we can't store any mass there. So all that mass has to go back out. So it's essentially conservation of matter. You can't just have those go away. That's what KCL is. And algebraic means including direction. That's all it really means. So here are a couple different forms, right? Current in is 0, current out is 0. Well, the current in equals the current out. Like I said, I like to do the last one, but if you work through all the different ones in here, you'll see you'll end up with exactly the same result. The current in equals the current out. All right, let's do a KCL equation. So we want to calculate the current through R3, which is this current right here. If it is known that the voltage source right here supplies a current of 3 amps. So this is a perfect application for KCL because we know the current here has to be 3 amps, right? That's given in the problem description, which means that current is 3 amp, right? Because we can use KCL in this node, say that the sum of the current in equals the sum of the current out. The current into the node is 3, so the current out of the node has to be 3 as well. And so summing those two, or setting those two equal to 0, means the current out, IR1, equals 3 amps. Now, I'm going to just go ahead and draw things hopefully pretty simply. I have 3 amps going here. I have 2 amps going here. I have an unknown current going here. And I have 5 amps going in here. So using that term, the sum of the currents in equals the sum of the currents out. The current in, 3 amps, plus 5 amps, equals the sum of the current out, 2 amps, plus I, means 8 minus 2 equals I, which equals 6 amps. Pretty straightforward, hopefully pretty easy way to do that. Let me just double check to make sure I'm still recording. I am. All right. So that's an easy KCL, but we're going to start expanding on it. We're going to start using that more and more. So you can actually start to see, hey, where do I get all this information from? Now I'm going to do KVL, which requires the concept of a closed loop. And why is it a closed loop? Because the concept is, if I go back to that point, my starting point, the voltage that I should be there should be exactly the same when I started. So when I go around my entire loop, if I start at point 1 and I get to point 2 and I haven't connected those yet, those voltage points should be the same. I can't have a potential difference across a 0 ohm, connection. So KVL is essentially conservation of energy. I'm going around that loop and I'm not putting any more energy into that specific location. So I've got to go ahead and do that. Now, again, this is another thing where I need everybody to understand. There's 2 ways to do this. Item number 1 is the sum of the voltage drops equals 0. Or item 2, the sum of the voltage rises equals 0. They're essentially the same thing, but it's important that we understand which we're using here, because when we identify conventions, pluses or minuses, we use a different approach. So how many here use item number 1? Who use item number 2? Who's not sure? If you were an EET student, it's fairly confident that you did the sum of the voltage drops. Because if I look over here, V1 in my current direction, so I'm assuming a loop current in that direction. So V1, in the direction of current, I go from a lower potential to a higher potential. That's a voltage rise, isn't it? But a voltage rise is not a voltage drop. It's a negative voltage drop. So that becomes negative V1, right? A rise in voltage is a negative voltage drop. So we call that V1. In the direction of assumed current flow, our V2 goes from plus to minus. So that is, in fact, a voltage drop. And in the direction of our assumed current flow, we see that our voltage 3 goes from a lower potential to a higher potential. So that's a voltage rise. So we end up with that there. That's if you use item number 1. If you use item number 2, you're going to end up with the same numbers ultimately, but most people are more comfortable using the sum of the voltage drops is equal to 0. Does anybody have any issue with us doing it with some of the voltage drops? Because again, most likely that's what you were taught here. And then depending where you were, it really just depends on, what the instructor used, but that's typically how we do it here. Again, if this becomes a problem, we can change this convention, but the reason why we spend enough time at the beginning is to make sure that we're all on the same page. A plus is this reason, or a minus is this reason, and we talk about it that way. So here are the two approaches, but the paths are essentially the same. All right, so we're going to do a little more work here. We want to go ahead and apply KVL to solve for VR2 and VX. So how do you do this problem? Anybody want to give me a hint where to start? Yes, sir. Okay, so what does that what does it tell me? So start there, and then what do I do with it? Do I write a loop equation around it, or around what? Okay, where's the loop that you propose?
36 volt source R2 and the 4 volt there. There's a loop.
Yeah, right here. This is a loop, isn't it? It's a closed loop. So I can do a KVL around that closed loop. So is the 4 volts a positive or a negative in the assumed direction of current?
Negative.
I go from plus to minus. That's a voltage drop, isn't it? And if we're summing voltage drops, that's a positive 4, right? Because that's a voltage drop. The next case would be positive because it's the voltage rise, right? So if we're summing the voltage drops around a closed loop, a voltage drop is a positive, a voltage rise is a negative. So this, plus 4V, sorry, is a negative 36V. What do we do with VR2? Very important, because I've set in my circuit the plus and the minus here, I am dictating what I think is the potential, plus to minus. So is that a voltage rise or a voltage drop? Drop. So that is a positive or negative number? Positive number. Oops. And that equals 0, right? So VR2 equals 36 minus 4, 32 volts. Now that's really good. That was a great first start, because we now know VR2, which means we know that this is equal to 32 volts. Now we can do another closed loop. All right, so let's write the second loop equation. Is 32 a plus or a minus? Minus? Anybody have any heartburn that before we said it was positive? We called it positive over here, but it's negative over here. You have any issue with calling it positive on one side and a negative on the other? Why not? Keep saying. Yeah. In the direction of current flow, right? In loop one, it was plus to minus, so it was a voltage drop. In the direction of this loop, it is minus to plus, which means it's a negative number. So you can have positives or negatives as long as we go back to our convention, which is in the direction of current flow, is it positive or negative? All right, so plus or minus 12. Plus or minus 14. Plus or minus V2. Keep going. Plus or minus VS1. Oh, minus. Plus or minus VR1. Oh boy. We got one equation and how many unknowns? So normally we need three equations, right? Three equations, three unknowns.
Oh, it's all in, yeah.
So what does that mean? We can introduce another equation. What does Vx equal? Can do another loop there, right? So Vx, we're going to write another loop equation. Negative Vx minus V2 minus VS1 plus VR1 equals 0. So all this stuff over here can be replaced by Vx. So our equation becomes negative 32 plus 12 plus 14 plus Vx equals 0, right? Or minus Vx, sorry, I'm opposite. So my Vx value is equal to 6 volts. All right. So that's if we want to be very explicit and doing it all out. You could have also said, I don't really care, but all that other junk over there, I'll just replace all that other junk with an equivalent box and just call it the voltage across Vx. So if you want to do that extra step, you can, but if you can see it, then it just makes things a lot easier. Okay. But finding V2, VS1, and VR1 would be much more difficult because we need more information. All right, let's tackle this one. How would you do this one? IX and VX. Yes, sir. So let's add the voltages together. Even if they didn't have the same polarity, we could add them.
You could, yeah, you could.
You just would take the difference, right? That's 12. Okay, now what? Simple Ohm's law, right? IX, which is the current through here, is equal to 12 over 100. 120 milliamps. And then what is Vx equal to? It's 12 volts. We're just looking across the common term. So may have seemed a little bit more challenging when we first looked at it, but once you started making some simple substitutions, it gets quite a bit easier. Hopefully you see that. All right, now we're feeling good about ourselves. How about this one? How would you tackle this problem? Solve for Vx and Ix. Getting out the paper and pencil. there's really one important thing that you have to do to start this problem to have even a chance. What is it?
Superposition?
Can't do superposition because I don't know what IX is, right? How would you tackle this problem? Look closely at the current. Yes, sir, Luke.
Did you change the current source to a voltage source?
I can, but I don't see how that's gonna make it easier for me at this point, but it's possible. I just don't see how it's gonna make it easier. You go and then you go back.
Would it be an equivalent power? Because of the given amperage that we've got, given voltage.
It's possible, but the problem is we still have to go back to voltage and current, so I don't know if that's gonna save us any time. Luke?
Find the voltage drop across the 8 ohm.
Yeah. If I can calculate this voltage drop, don't I know that voltage here? So what is the voltage drop across the 8 ohm resistor? I times R, or 40 volts, right? And it's in the direction shown because we know that a resistor is always a load. That's never going to pump out electrons, right? That's always dropping. So now I have 40 volts. What's the voltage from here to here? 20, because I can do another loop, right? And I can end up with 20. So I've got 20. How much current is going through here? You were right. Yeah, you were right. 2 amps. Now I know the current through there. Do I know the current through here? How much? Can I calculate the voltage drop across here? 12 volts. What's the voltage here? Ding, ding, ding. We have our first part. Now, what if I calculate the current through here? What is it? The current is 16? 4. Then my last thing is current in equals current out. How much current out? 6 is current out of this common node. I see my current out is 4. And I got 3 here, so doesn't that mean I need, whoop. Definitely not I amps. 1 amp from there. So this was a combo. But what did you do? You all were thinking about it, and then the key was what Luke said, is finding that voltage drop. Once you find that, then you can find the next voltage, and then you can start to figure out currents and use the combination of KVL and KCL to walk through. You needed to use both, right? You couldn't calculate how much current was going through the 4 ohm resistor until you did a KVL loop and then a KCL for the node. And then you did that again, one more time, and you ended up with the final answer. So a lot of what we're going to do in this class is more complicated circuits like this, where you can't just do a Thevenin or, equivalent circuit with series parallel combinations. You're actually going to find that really messes things up. So you're going to try to stay away from that. But what we did over here is basic KCL and KVL. Questions for me? TV land questions?
No, this looks like review.
Yeah.
Did we go too fast today? You not know?
No.
Not too fast? Was it too slow? Luke, do you have a question or?
Yeah, the lab.
No lab tomorrow, yeah.
No labs.
No lab for tomorrow.
You have lab.
You don't even have to show up tomorrow.
Okay.
Having lab on the first week is always kind of hit or miss, so yeah, there's no lab. We'll probably have something next week, yes. Yeah, we'll start to do that, but in the interim, you should be working on getting multi-sim set up, because you'll be using that. And then also feedback, let me know if we're going too fast. This is the first quote unquote real class. Hopefully it wasn't too fast or too slow. Hopefully a lot of review, but it's getting you to think about things maybe in a slightly different approach.
So for the lab,
Are we using like primarily sim?
Primarily multi-sim, yeah, but you will do some stuff with Excel for nice looking plots and that type of stuff. All right, anything else in TV land?
I think we're,
Nice to see everybody's smiling face. Do you have a question for the class, or do you want me to end the class and? Okay, all right, I have a student here with a question, so have a great day and weekend, everyone, and I will see you all next week. Take care.
all right, thanks,
Thank you,
Paul.
Paul.